also is currently a General Secretary of NRNA. I think it's really our pleasure to have him, Sharma, in our conference as an invited speaker. And then I think today he's going to talk about the physics, but I think it's good to have him on board and the ANPA, and then just to talk about what the ANPA can do in the physics research back in Nepal, and then not only from the physicist point of view, from the non-resident Nepalese point of view too. So let's welcome Dr. Hem Sharma.
Thank you, Quasicrystals. Namaste and good day, everyone. Good evening, good afternoon, good morning, wherever you are. Well, thank you, ANPA, for inviting me to present my research. Close my camera if I can. Okay. Also, I appreciate the colleagues who are involved in ANPA for bringing Nepali physicists in a single network. Especially, I have seen many young physicists. I believe a forum like this will certainly help to share knowledge and experience with each other, not only in USA but also outside, like me. And I hope that will also inspire physics education. The area of my research is surface and nanoscale physics of complex materials, particularly quasicrystals and intermetallic alloys. The goal is to obtain atomic scale understanding of physical phenomena, which are important for technological applications, such as catalysts, coating materials, and surface applications. We also use quasicrystal as a template to grow thin film of metals and molecules. Again, here the objective is to fabricate atomic and molecular overlay with novel structure and hoping to have a novel physical properties, such as quasicrystalline structure of single elements, like shown in this picture here, laid on deposited on a specific quasicrystal, or molecules like C60 or pentasine deposited again on the quasicrystal surface. I'll come back to this these results in detail later. Currently, we are extending our research to large-scale quasicrystalline structure, such as quasicrystalline metamaterial fabricated by three-dimensional frames. Well, let me first introduce my university research group. Since I'm outside of Europe, USA, I'm not very familiar. Liverpool University is located about 200 miles northwest from London. It is one of the oldest and largest universities in the UK, which has about 25,000 students studying faculties and 35 departments. It is a member of 20 Russell Group universities, which are research-based universities. This Russell Group University includes the University of Cambridge, Oxford. In physics department, we do a wide range of research: physics, nuclear physics, condensed matter physics, surface science, astrophysics, and recently we have established a National Innovation Factory in collaboration with chemistry department, and also sometimes if there is a new institute on renewable energy, people are mainly working on photovoltaics. Again, this is in collaboration with engineering and chemistry. Well, myself, I belong to condensed matter physics, and this university is linked to 9 Nobel, that is quite some time. Well, I have 4 PhD students, Oscar and Naima. They are progressing to second year now. Dominica and Amna, they are progressing to final year. I have on-site collaboration with Professor Magrat, department, and with Esther in engineering department for the new area of research, quasicrystalline metamaterial. I also have active collaboration with various institutes group for European network of complex metallic alloys. Also, the collaboration, for example, with the University of Science with Samura, Dr. Quas. Dr. Quas was my PhD student. He moved there for a postdoc. We are experimental group, so we have to collaborate for theory. For that, we have working with Dr. Nozawa in Chicago. Okay, let me introduce what are quasicrystal in a simple term I can. Conventionally, solid materials can be divided into two groups, the amorphous and crystal. In crystal, atoms are arranged in periodic order, one dimensional, and they exhibit a specific symmetry, namely trivial one-fold, two-fold, three-fold, four-fold, and six-fold rotation. And the symmetry is reflected in atomic scale, like in the square, or in the macroscopic scale, like in the rectangular phase of the crystal. Whereas in the amorphous, atoms are randomly distributed and they do not exist. Whereas quasicrystal, there are new type of solid where atoms may be distributed, for example, in one dimension Fibonacci sequence. The Fibonacci sequence is a mathematical sequence which can be obtained by generating two-line segment S replaced by S and S replaced by L. Just have to follow some rule can generate a sequence. The interesting thing is the ratio between these two-line segment is an irrational number, tau, or golden mean. It's a kind of characteristic number often appear in class. It will also appear in microscopic. But in two-dimensional case, the atoms in quasicrystal may be located at the vertices of a geometrical tiling. For example, famous Penrose tiling, which is formed by tiles of you can extend your concept to a higher dimension, just thinking about locating every dimension. And quasicrystal often poses rotational symmetries which are forming in periodic crystal. For example, could be 5-fold, 10-fold, or 12-fold. Well, we know from our textbook, this 5-fold symmetry or 10-fold symmetry is not allowed in periodic crystal. This is because I read this line from a textbook of Quasicrystal crystal. It is not possible to fulfill all space with connected area pentagon. That means if you try to build or cover a space using pentagons, you always end up with gaps. The simple reason people thought the 5-fold symmetry was not possible. Whereas if you have an hexagonal symmetry, then there are no gaps. Despite this conventional thought, Dan Sheckman and his co-author discovered a new phase in aluminum manganese alloys, which shows discrete diffraction pattern like this one. You often see this discrete diffraction pattern. But interestingly, it has 10-fold symmetry. And when he discovered, and he was quite sure about it, like really a 10-fold, and really turns out to be a 10-fold. So this new type of solid materials which are long-range order or produce diffraction, discrete diffraction pattern, but no periodicity are called quasicrystal. So the discovery of quasicrystal was awarded Nobel Prize in Chemistry. And what you may remember, I organized a conference in Nepal and invited him and also in this department. The quasicrystalline phases are stable in a very narrow compression range. For example, for common aluminum, palladium, manganese quasicrystal, and it is stable only around this region. That means should have around 70% of aluminum and 15% of platinum and manganese each. Well, this is because the ratio between valence electron and for atoms should be specific for the specific class. So, if you're working on alloy materials, in order to fulfill this immediate criteria, it has to have very specific. Move slightly away from this region, then move from quasicrystalline region to other periodic. So normally, the quasicrystals, not normally, in almost all cases, quasicrystals are grown in lab with a precise composition and precise growth condition. But very interestingly, some scientists from the USA and they discovered quasicrystal in a rock in Russian mountain. That's simply accident. There are some examples of quasicrystals in nature. As so the structure of quasicrystal can be explained using clusters of atoms. Here I have shown one example of silver indium quasicrystal, which I'm using for my research. This can be explained by using 5 tetrahedral cluster. It looks quite complex with the 5 cells combined together. So if you pack these clusters at the body center cubic lattice, like here, you end up with a periodic crystal with giant unit cell, and this is the period you can see from the passage crystal here. But we call this is approximately quasicrystal, not real quasicrystal, but localistic is very similar. But if you pack the same clusters on the 3-dimensional plane for starting, you produce quasicrystal. But of course, in this case, you need to fill a gap in between clusters, call these atoms atoms. But about more than 90% of atoms belongs to clusters, and the rest can be also predicted from. Again, small small chain chemical composition from 30 to 40 is from crystalline structure. So I'm trying to indicate that the quasicrystals are often very complex in terms of structure and chemistry. So we like to have as simple as possible quasicrystal history. Okay, the first discovered quasicrystal and most of the quasicrystalline phase have been observed in alloy materials, but there are other materials which also show quasicrystal. For example, some polymers, colloids, even perovskite materials they can have quasicrystalline structure. Some molecules may self-assemble in quasicrystal. In this two example, we have shown that if you deposit a periodic material on the surface, some molecules on the quasicrystal surface, you may grow quasicrystal. I'll come back to these two systems in detail later. So in terms of physical properties, like structure, they exhibit physical properties. What they are metallic alloys, but they have a high electrical resistivity. They have radius density Fermi level, usually in metal. That's how we call the pseudo gap. They are very brittle compared to ductile metal. Have low surface strain energy comparable to Teflon, low coefficient deflection, and hard material comparable to. So some of these properties are important for technology. Coating materials. Some quasicrystal have shown higher stability and higher reactivity. These two important chemical reaction, production of hydrogen energy. So they are important for environment and energy point of view. The potential for hydrogen storage has been also tested in some quasicrystal, and we found that they have a higher storage capacity. But again, they teach how to release hydrogen. For us, we are interested in surfaces because some of these physical properties or potential application are surface phenomena like watching materials. So to optimize this physical property, you have to understand the surface. So that was our primary motivation why we started investigating surface. So for quasicrystal surface studies, we need two things. One, we need large single crystal like this one here, and also we need the ultra high sample. Since well, these samples are not available commercially, we have to rely on our collaborator and especially the sample from USA or Germany. So once we have the sample, we slice our sample along the desired crystal pathways. The three possible axes, for example, in a five-fold mass interest. So we have studied two-fold and three-fold. Once we slice it and polish using diamond test on tiny, and we put the sample in ultra high vacuum chamber, spatter any of the ion bombardment several times. So once we think the sample is ready, and then we transfer the sample in characterization chamber. We use various experimental techniques to characterize, like scanning tunneling microscopy for structural characterization. But for chemical characterization, we have to use another. So once we characterize surface is ready, then okay, I just wanted to show the glimpse of yeah. So if we prepare surface, it's a suitable condition, it can produce terraces as shown here. So these are the technically flat terraces separated by depth. So it's a base terrace that corresponds to specific fault plane marked in this picture here. This plane is correspond to high density plane, as usually think surface always from high. And also these planes intersect the clusters. The low energy electron diffraction comes from the long range hyperload. With STM, well, we may be working on STM capability to resolve structural mechanism. So it is the dots of diffusion you see here, that's corresponding. Well, this was taken positive bias. Well, in any case, we have studied many quasicrystals, so we can make one single conclusion: the surface current and some system relaxed. So it's easy for us to respect. So once we have clear understanding of the clean surface, we deposit it in various metals. Periodic table I have marked three elements we studied. Again, just to summarize what happens if you deposit periodic substrate and quasi-periodic materials or anything on the quasi-periodic substrate, you can various things happen. The first thing, most deposit elements grow in periodic fashion. So in this case, I have this periodic domain rectangles aligned along 10 regions. These 10 for 2 structure. They are not real quasi formed by 10 periodic. So there's some elements like copper and cobalt that grow in materials. Those are separated by famous example of quasi. There are only few elements like bismuth, antimony, tin, lead. They may grow in quasi. Example in this, you can see the nice pentagons there. This is formed by 5. If you deposit more crystal on the surface in a controlled manner, then you grow the close spin. So it's in a larger scale, the green products a single layer was in other part. So what happens if you put more surface on the more elements on the surface? Then you start. Again, you can already guess it. theory regarding that. So using STM, you can really see how it goes. You can see some islands are more stable than others. This island disappear and this will go. So this the stability of specific islands is due to quantum confinement. Okay, in most cases, we saw quasi structure of the one atomic layer, but in the rare case, we have demonstrated, or we are the first to demonstrate that quasi-line structure could be extended up to three atomic layers. Here's one example we published ago. Again, this lead deposit, another quasi-crystal here. You can see this nice small pentagon. This is the pentagon first layer, and then your larger pentagon second layer. If you put more lead on that, then space will fill and you see like complete patterns. And if you have enough material, you see this then network of pentagons you can map using pentagon. Well, we always use like a Fourier transform analysis of this is the third layer and so on. Okay, again, we ask our collaborating and check whether our interpretation of the bias is correct or not. And happily, it was experiment for giving us them. What is happening here is a simple term. As I said, these are the clusters are used to explain the structure of the bulb. We form a surface. Basically, what happens? The surface bisects the cluster center. You have like a half cluster. You have that kind of back and side. So if you deposit the lead crystal or the element, you simply sit on the back and side. So that's basically mirror, lead mirror the underlying half cluster. It's a simple sum, but real structure is complex. The interesting thing here is if you see the distance between the lead atoms and various height, they are comparable to the lead distance in FCC. So this distance is strong enough to stabilize such a complex structure with Quas. So here are some examples of molecules. For example, we deposit a C60 on various Quasicrystals. One example. So these protrusions here, dots, that's correspond to single C60 molecules. Here you can see two different types of molecules and darker molecules, lighter molecules. Darker molecules are center located at the center. You see many pentagons. Again, if you deposit more C60 molecules, goes layer and can map the structure. Can map the structure using planning. As usual, we use Fourier transform and also confirm that C60 molecules. I think someone has to mute the microphone. Okay, thank you. So as usual, we do the Fourier transform analysis and autocorrelation to confirm that. So what we found here, the C60 simply select the specific size of the surface. This case, C60 items of two different types, two or three different types. If you are using, for example, C60 and element manganese, C60 will go to the manganese side. And this is because there's an electron transfer thing where it's no theoretical calculation yet, but the thing is that electron transfer between iron and textile body. That's if the still interaction between iron or manganese with. Again, here if you compare the size of the molecules and distance between the additions, right? They are comparable. So we think that the both electron transfer and then size of the molecule are the governing factors for output of such a complex molecular array. So, so far I showed you all examples of quasi-square structure, but with 5-fold and 10-fold structure. But 2 years ago, we demonstrated for the first time that there might be a physical system with quasi-crystalline structure but with 4 folds. This happens again when you deposit C60 on another type of surface, 2-fold element. So here you see when you deposit C60 on the 5-fold surface, this picture basically shows distribution of magnetization where you see C60 on 2 different surfaces, 5-fold one, which is interesting, 2-fold one. So your C60 will simply go and form a pentagonal tensor starting, which I just now. But if you do the C60 on the 2-fold surface, then C60 will go on the manganese side of the new structure we call Fibonacci square time. This is the mathematical time predicted some time ago, but nobody really detected 4-fold scenario. So I'll explain a bit what is Fibonacci square charting. So Fibonacci square charting basically formed by 2 identical Fibonacci sequences superimposed after. Well, again, in Quasicrystal, we always don't talk about the unit cell, but we talk about its tiles. So in this system, we just need 2 different tiles. So each quasicrystalline because I superimpose 2 different sequences. But if you rotate this by 90 degrees, it produces the full identical tile. That means that it has proportion. There are different ways to check your symmetry. You can experimentally, you can do it in fraction, or in theory, you can do the Fourier transform. For symmetry, the but are not distributed in a theoretical order. They are distributed in quasi. So we basically this distance on that distance. So let's see how we obtain the distance. Again, this is ST image taken off a C60 equal surface. This sphere corresponding to 60 molecules. 60 molecules are located at the vertical square frame this time. But you may see that some molecules are not aligned. But if you reflect your Fibonacci pattern, then you found all of the 60 molecules. So again, here is scaling factors. That's up to the characteristic of. Okay, I'm almost done.
Sir, 5 more minutes.
Okay, so again, the Fourier transform and the theoretical calculation come from symmetry of the system. In same analysis, the autocorrelation, assume autocorrelation model and compare the happy consistent. Okay, just to summarize my talk, I showed you a novel structure can be formed when you deal with molecules or periodic materials on the surface. For example, I showed you the first observation of 3-dimensional quasi-crystalline thinking of single elements with complex structure. Also, we are the first to show you the quasi-crystalline structure of molecules like the C60. Also, so the quasi-crystalline structure before. We also propose a mechanism why such a structure form, and we think that the comparability of size of the aperture rate, separation of also electric transmission govern physical factors that Well, our finding have various implications. For example, molecules can be used as a chemical tool that can adjacent sites for complex structure that may help to understand these structures better. Well, this might also help to produce our molecular area of magnet. For example, if you drop C60 with a magnetic elements and people substrate, for example, in was one area. But it is all of the area we got very nice, beautiful pictures in ST. But when you want to make them more applicable, or if you want to study more physical properties, there are lots of limitations. Real, really good much with this. So that's why we're trying to move to new area inspiring from the current work that we want to produce the quasi structure, the larger scale micrometer, simple fabricate from centimeter scale using, for example, that's one of the areas we're trying to get. So that's right. So that's will help us to understand the physical possibility. The last, I want to advertise you the second Global Knowledge Convention, second another Global Knowledge Convention, is to be held in Kathmandu, but it's most likely online version. Well, I'm the chair of this conference. Dr. Hori Dar is a co-chair. Luckily, we are both are physicists leading this conference. It's not a physics conference, it's every area. We have 5 plenary session and creativity project session. There's only one session which is close to physics, not physics. We call intersection sciences. This is coordinated by Dr. Tara Sigdal. You know he's in USA. Dr. Naran Adhikari, so there will be a coordinating session. So you're invited, since it will be online, please submit extra. Hopefully, I'll see you. Thank you for speaking.
Thank you, Hemra Sharmaji. For a question, if you have any question, you have 5 more minutes. And then ask the questions.
Should I
सबैलाई म्युट गरिदिनुस् अनि जसको क्वेसन छ उसले he's gonna
Sir, I want to ask. Sir,
any questions?
Yeah, I want to ask one question.
Yes, go ahead, sir.
Okay, thank you, Emrah sir. Very nice presentation. I have the one or two questions actually. You are talking about certain gap found in the quasicrystal in DOS. So what kind of gap is in quasicrystal DOS? And what is the difference from the normal crystal to the quasicrystal one? And another one is you are talking about the Fibonacci multi-layer of the copper and the cobalt. Uh, does it follow the Penrose mapping or not in the Fibonacci series and others? And third question is, an atoms occupies in the cluster size, and what kind of that cluster size is it? Is that so that atom occupies that size?
Okay, I'm not quite sure I got your first one was some disturbance, but I'll start replying the second question first. For the Fibonacci sequence and Penrose starting, there are 2 different examples of quasicrystal. If you're talking about the 1 dimension, you often see like a Fibonacci sequence. But if you are 2 dimension, Penrose starting. Of course, there is an interlink between. You can always find Fibonacci sequence in Penrose starting. So in the particular system, we are studying copper. on aluminum, palladium, manganese. The Chinese study only the United States. So in one direction, we have atoms are arranged theoretically, but this you see the separation of atoms is from the Fibonacci sequence. As far as the position of atoms in the cluster, well, as I said, what happens, the atoms does not go to new sites. You have a full cluster. When you surface, the half cluster will be gone, so you have a vacuum here. But the system remember these original clusters and simply just go this side. You haven't really identified any new atom in between. It's very difficult with our again, as I said, the density of the sites is very low, so I think with the SQ will not be able to identify. I think your first question you're talking about the pseudo gap in the electronic states, or
Yeah, what kind of gap? Means you told some gap is found in Quas and yeah.
Okay, well, first of all, this is not our work, but it's commonly, if you say metal, for example, you have some demonstration formula. But although these alloys are formed by metals, if you calculate or measure them, we call radius density. It's not in the range of milli-electron volts. Even if the room temperature may not be expanded milli-electron, like semiconductor. But it does, people believe that the figure has related to anything. That's still
Okay, one more question.
Thank you, Embracer.
I have one question. So, how do you explain this phenomena theoretically? I assume length is an old partition, right?
Sorry, can you repeat it?
So, how do you explain this quasi-crystals in terms of theory? I mean, does a band theory?
You mean in terms of structure? Okay, well, I mean, there's no answer how the quasicrystals would form that, but there are various models people have been used. Well, most common and famous model to predict structure is the higher dimension concept. Well, in terms of physics, we don't really know why such a complex structure form. But in terms of predicting structure, you can study the higher dimension concept. For example, starting with 6 dimension mathematical space, which is a period structure. It has like a some kind of DCC or FCC structure. You can always project that structure in a physical space in 2 dimensions. You can always predict. That's the only method you can use to characterize it. So as far as why this project should become, I don't think that has been. But it's very, very intriguing because to combine the identification quite easily when you grow the sample, but combining different types of styles, it's a very, very mystery. The nature is very mystery.
Okay, let's thank the speaker, Dr. Emra Sharma. Thank you for accepting our invitation and giving a talk in our ANPA Conference 2020. Hope to see you again in the future.
Thank you, Pastor and everyone.
Okay, our next talk is by Gyanendra Dakal, University of South Florida. He's going to talk about the observation of distinct topological superconducting state and CaBi2. I believe you are handling Gyanendra. You can fire yourself. Hello?
Yes.
I think, yeah, you can play.
Namaste everyone. First of all, I would like to thank ANPA for providing me an opportunity to talk on my work. My work is the observation of distinct topological superconducting state in calcium bismuth. The condensed matter physics is understood on the basis of spontaneous symmetry breaking. However, recently it has been studied on the basis of topology. Let's begin our talk with classical Olympiad. It is a common phenomenon in conductor when it is placed in transverse magnetic field, and due to Lorentz force, the moving charges produce potential difference perpendicular to both electric and magnetic field. The second one shows the quantum Hall effect. Is the quantum version of Hall effect in 2 dimension. When 2-dimensional electron gas is subject to a strong magnetic field, the longitudinal conductance becomes 0, while the quantum plateau of Hall conduction is equals to n square over here, as shown in the third figure. Let us assume a condition that a charged particle is allowed to move in a uniform magnetic field in 2D. It is equivalent to the harmonic oscillator and energy is quantized. The number gives the lambda level, and which is called Char number. The Char number is related to the periphery, as shown in the right one. In the middle, electrons move with cyclonic motion, but at the edge, they cannot complete the orbit. That's why, and the time-difference symmetry is broken. That's why they cannot move backward. So they have only one direction. Because of this reason, the electron can move only one direction, as shown in the figure on the right side. And the third number shows the topology of this material. Let's talk about spin quantum Hall effect. In spin quantum Hall effect, you don't require magnetic field, and this behaves as 2 quantum Hall effect. And in this case, the magnetic field is obtained from the spin orbit of another system. That's why time reversal symmetry is protected, as there is no intrinsic or extrinsic magnetic field. And another thing is, in this case, there is no charge conductance. Rather, it conducts the spin. And spin orbit coupling behaves as the magnetic field. And in this case, Char number is not a good number like in quantum Hall effect, because in this case, time reversal symmetry is protected, and Char number gives the condition of time reversal symmetry broken condition. That's why we require new criterion that's called G2 indices. Let's talk about paradoxical material in which the bulk behaves as an insulator and surface behaves as conductor. Interestingly, the spin are polarized. For instance, if a right moving electron has spin down, left moving should have spin up, as shown in the figure. In terms of band structure, the bands are linearly dispersing and the bands are inverted. The surface state exists at the band gap, and the band gap are opened by spinor coupling. In 3D topological surface state, it is characterized by Dirac cone, as shown in the figure. The topological materials can be used for quantum computation, spintronics, memory devices, etc. In order to determine whether the material is trivial or topological in 2D or in 3D, we use G2 indices, popularly known as Hocken indices. So in 2D, we introduce nu, which is similar to Char number or the TKNN. And if nu equals to 0, then the material is trivial. If nu equals to 1, then it is topological. Whereas in 3D system, it is a little bit complicated, and we require 4 indices. The first one represents strong Ti. If nu not equals to 1, then it's strong Ti. If it's 0, it could be either weak Ti or trivial. And those last 3 indices represent weak Ti. If they are non-zero, then the material is weak Ti. On the right side, another way to determine weak and strong Ti is by counting the number of Dirac cone in a Brillouin zone. If a Brillouin zone contains even number of Dirac cone, then it's a weak Ti. If it has odd number of Dirac cone, then it's strong Ti. Since Foucault criterion is not sufficient, That's why new criteria have been defined, which defines a lot more materials on the basis of their space group. And these are not only based on the inversion symmetry. And recently, large materials have been predicted to be topological. That's why almost 30% materials of all the materials studied have turned out to be topological. We were interested in a superconducting material which shows sharp Meissner effect at 2 Kelvin, as you can see on the right side, this graphs. And it has a square net of bismuth and corrugated calcium and bismuth atoms. And calcium bismuth crystallizes in orthorhombic lattice, and its space group is 62, and its non-symmetric symmetry. We studied transport property of this material, and it shows metallic behavior with decrease in resistivity smoothly while decreasing the temperature. And residual resistivity ratio is quite large. It indicates the good quality of sample. On the right side, we show the magnetic resistance plot, and it shows that high magnetic resistance, similar to WT2 and GRSS type of material, and the magnetic resistance shows the non-saturating value, and it reaches around 7,000 percentage at 2 Kelvin. This indicates this could be an interesting material, or it may have some topological origin. On the left side, we saw this conventional billion for calcium bismuth, and we have noted the high symmetry point, and the blue color structure shows the 2D projection of 3D billion. And on the right side, we saw the bulk band calculation of calcium bismuth, and in that one, we can see some bands are crossing the Fermi level. That indicates this sample is metallic. However, there is a band gap between these two blue bands that it also indicates on the basis of a band calculation, it equally can be taken as an insulator. And this is the website we normally look upon whether some material are topological or non-topological. It's highly recommended to check one. The another thing is, in this one we check the symmetry pattern, and in this one G4 shows 0. That indicates it's not a strong TI. And there are two indicators, and they are not 0. That means it's a weak TI. This slide contains our main RPS result, and in the first figure we show Fermi surface map and energy contours. The Fermi map shows that the central diamond-like structure. You can also see a diamond-like structure at the A point, and the energy contours show the evolution of band structure with binding energies. The right side shows the schematic drawing of the Fermi surface. We show dispersion map along the AGA direction, the bottom figure on the left side, and where you can see two distinct bands, alpha and beta, and both are linear. And you can see the alpha band crosses with another alpha band. They cross at 530 MeV below the Fermi level. And in our case, we always look for the linear band crossing. That is the signature of topological insulator. And if you see the right side and the bottom side, then it shows that the dispersion maps are taken at different photon energies, and alpha band doesn't change its same band size with the photon energy. That indicates the surface nature of the band. Now we look upon other directions, and along this X, gamma X, and gamma M direction, and in these directions we also can see some linear band crossing, but they are not topologically significant. That is why the spectra we see is not strong enough. In summary, we report the observation of topology surface state in our superconducting material, where topology is defined by the symmetry indicator. At last, I want to thank my professor, Dr. Madhanepani, and all my colleagues for helping me throughout this project, and to you all for listening to my talk.
Thank you, Ganendra. Do you have any questions?
Can I have a question, please? I hope I'm audible.
Yes, sir. Go ahead.
Okay, thank you. So, Gyanendraji, thank you for the very nice talk. And actually, I have two questions, which is related with one thing related with the Z2 indices, and the another with related with the Dirac state that you have observed. So, if I understand correctly, you mentioned that this material, the single material itself, shows properties, right? One property is the topological state, topological insulating behavior, and the another shows the Dirac behavior. Is that correct?
No. So if you take 3D topology insulator, you have Dirac cone along. It's like a conical shape.
Yes, in one of the direction, right? So not in one of the direction you are having a Dirac cone-like state, and on the another direction you have a gap-like feature which indicates the weak topological insulating state, right?
The Dirac cone exists within the band gap. That's why it's topological insulator. If
Okay.
it's a 3D Dirac cone or a topological Dirac same metal, then we don't have band gap. Rather than it would be made with bulk bands.
Okay, I see. So as a whole, what I understand at the moment is that this system is a Dirac semi-metal, which has a Dirac crossing-like features somewhere close to the Fermi level.
No, it's a topological insulator.
It is a pure topological insulator.
Yes. If it's a Dirac same metal, the Dirac cone would be formed by bulk bands. And in our case, they are formed by surface bands. That's the difference.
Yeah, so that was my confusion actually. So can I see your Dirac state slide? Because there you have shown a very nice RPS measurement wherein it looks as if it is a Dirac state.
Madhav sir, this is a recorded talk, so he probably can send you a personal message to you. So let's thank the speaker for now, and then we can have a session later on.
Okay,
maybe we'll discuss on that.
Yeah.
Thank you.
Our next talk is from the same institute, University of Central Florida, Sabin Ray. He's going to talk about the temperature-dependent electronic structure in a higher order topological candidate UIN2AS2. So, Ganendra, I think you have a presentation, right?
Yes, I have.
Okay, can you play, please?
Greetings to everyone. I am Sabin Remy from Neopane Group at University of Central Florida. Today I am going to result.
I think we can see the screen.
Ganendraji, I don't know if it's your computer or somebody else. Is there a resolution problem?
Probably yes. Just a moment.
Yeah, also, actually, in Garendra's case, I couldn't hear him properly at all.
Okay, how about let me share it from my side? If it...
Oh, okay, I'll make you.
Yeah, your resolution had a problem.
I'll make you. Sorry, present.
So, so everybody okay with this one?
I think the
Yeah, it
sound
looks good.
I think the volume is not good.
Yeah, but I think there is also reverberation, like you can't hear properly. Words are not
Yeah.
clear sometimes.
Maybe you need to increase the volume of the computer or the laptop that you are using, probably.
Oh, it's fun. Now it's better, actually. It wasn't really good during the Ganendra's talk. Sure.
no sound.
No sound, not audible. Sorry.
Where is that? I forgot. Yes, let's try this one.
Yes, too. Before going into the reason,
It's coming.
I think we can see now, but it's gone.
before going into the results, I want to discuss about some theoretical backgrounds, starting from topological insulators. These are the materials which are analogous to the band insulators in the bulk. However, on the surface, they have gapless surface states within the band inverted valence and the conduction band. These surface states are linearly dispersing on the momentum space, and these spin states are locked to the momentum direction. The surface states are protected by time reversal symmetry, and they are robust against the perturbations as long as this symmetry remains protected. And these topological insulators are characterized by the G2 topological invariant. However, it has been shown in many cases that such kind of gapless surface states can also be protected by some crystalline symmetries, and such kind of topological insulators are called topological crystalline insulators. In common, these topological insulators feature the surface Dirac states on the d-dimensional d-1 dimensional edge of the surface state. For example, a 3D TI would have surface states on 3-1, that is 2-dimensional surface. Recently, a new kind of TI is on the scene, which actually does not follow the same bulk boundary correspondence as the conventional TI, and such a kind of insulators are called higher order topological insulators, HOTI. A kth order higher order TI in D dimension has a surface and the bulk gap, but it hosts gapless modes in D minus K dimensional region. For example, a second order 3D TI will have a topological states on the 1D hinge of the crystals. So here we can see an example of second order 3D TI bismuth, where on the left bottom figure we can see on the clip surface there are two types of edges denoted by blue and red lines, and on the right figure the differential conductance map obtained from STM measurements we can see on the type A edges there are edge states. Implying it is a second order 3D TI. So fascinated by this, we search for a material which potentially has this kind of novel topology and an intrinsic magnetism as well, so that we can study the interplay between the non-trivial topology and magnetism in such materials. And the material we found was UIN2AS2. It crystallizes in space group 194 with hexagonal lattice. The lattice parameters are as shown. Very large C compared to the in-plane parameters makes 001 surface a natural cleaving surface. So on this figure, we show 001 surface prevalence zone as well as the bulk prevalence zone. On the resistivity measurement shown here, we can see a sharp peak at the antiferromagnetic transition 16 Kelvin. And on the code level spectrum, we can see clear peaks of EU 12 and AS3D, showing the good quality of our samples. So below the AFM transition, this crystal can have almost energy degenerate two configurations. One is AFM-B, in which the magnetic moments are in plane, and the other is AFM-C, in which the magnetic moments are out of the plane. So we also performed the first principle band calculations, bulk band calculations, we can see here. And in the absence of spin orbit coupling, the valence and conduction bands dip into each other, thereby creating band inversion at these positions along gamma M and gamma K. However, in the presence of SOC, the valence band and the conduction bands are separated, thereby creating gaps. We also calculated the parity-based GFO invariant by using this formula here, and we got GFO equals 2 for both the AFM configurations, implying EUI into AS2 is an XII insulator in both the configurations. Our theoretical analysis showed that there are two mirror planes, KY equals 0 and KX equals 0, with non-zero Chern number in AFM-B configurations, and they protected a gapless topological state. Therefore, in AFM-B phase, EUI into AS2 is a topological crystalline insulator. However, in the AFM-C configuration, there is no symmetry protection and the surface are gapped out, and EUI into AS2 system realizes HOTI phase with GFO equals 2. Next, I move on to the results from our ARPES experiments. The upper panel shows the Fermi surface and the constant energy contours at various binding energies. At 22 Kelvin, that means in the paramagnetic phase, and the lower panel shows the data in the antiferromagnetic phase at 8 Kelvin. In the paramagnetic phase, there is a single circular energy pocket which grows with increasing binding energy, implying the whole nature. In the AFM phase, in the lower panel, the whole pocket is still there. Apart from that whole pocket, we can also see an extra inner circular pocket here, which is more visible in this 50 MeV energy contour. This extra feature also grows in size and merges with the outer feature at around 300 MeV below the Fermi level. Further going down, the binding energy, we can see a bulk rectangular feature appearing in both paramagnetic and antiferromagnetic phases. Here I present the dispersion maps in the paramagnetic and antiferromagnetic phases, consistent with the features observed in the Fermi surface and energy contours. We can see a single whole band in the paramagnetic phase and the splitting of the whole band in the vicinity of the Fermi level in the antiferromagnetic phase. So these features can be more clearly visualized in these second derivative plots where there is clear band splitting in the antiferromagnetic phase. So in order to better illustrate the change across the antiferromagnetic transitions, here I present the second derivative of the energy contour, where we can see a clear inner pocket in the paramagnetic phase. In the momentum distribution curve as well, we can see two peak features in the AFM phase, while a single peak in the paramagnetic phase is indicated by these black arrows. We also calculated the approximate position of the Dirac point in the paramagnetic phase by fitting the peak positions on the MDCs, which we found was 320 MeV above the Fermi level. To confirm the disappearance of the inner band in the paramagnetic phase, we also performed measurements at 46 Kelvin. These are all measurements at 46 Kelvin, and similar to the data at 22 Kelvin, we see that there is no extra feature apart from the whole band in the vicinity of the Fermi level. In order to see if we can reproduce the change in band dispersion across the antiferromagnetic transition by theory, we also perform the surface calculations for AS terminated 001 surface. In the paramagnetic phase, a doubly degenerate non-trivial whole band crosses the Fermi level, forming Dirac cone state lying above the Fermi level. Below the AFM transitions, we can see both AFMB and AFMC give similar energy dispersion in the whole dope region. However, if we see above the Fermi level, AFMB phase realizes a type 2 Dirac cone above the Fermi level, while in AFMC we can see there is clear gap in the surface states, which is consistent with the earlier argument that UI into AS2 is TCI in AFMB phase and IHOTI in AFMC phase. We can also see the band splitting is reproduced in both AFMB and AFMC phases. In conclusion, we studied the electronic structure evolution of UI into AS2 across the magnetic transition. The parity-based G-photological index showed in both AFM phases. UI into AS2 is an axial insulator, plus in AFMB it is a TCI, in AFMC it is HOTI. Our surface measurements showed the splitting of the whole band in the vicinity of the Fermi level, ongoing from paramagnetic to antiferromagnetic phase caused by the lifting of the band degeneracy. Band splitting are reproduced in both AFMB and AFMC phases. Therefore, in order to identify the exact topological state of the UI into AS2, we need to study the nature of the states above the Fermi level by using time-resolved measurements. We also calculated the approximate position of the Dirac point in the paramagnetic phase. However, time-resolved measurements are necessary to accurately resolve whether there is actually a Dirac point or there is a small gap in state. So in the future, we wish to study the time-resolved RPS, spin-resolved RPS to resolve the spin structure of the observed Dirac bands and also the hinge state to reveal the 1D HOTI state. The experimental data were taken at ALS beamline 10.0.1. This project is supported by Air Force of Scientific Research, National Science Foundation, and Department of Energy. We also acknowledge our collaborators at Northeastern University, IIT Kanpur, and Police Academy of Sciences. Thank you.
Okay, any question?
Yes, I have a quick question. Sabin Regni, so I saw, so there is a shift in the dark, in a sharp feature at 46 Kelvin, something around that. So just left to the gamma point, then it was at the lower temperature you showed. So I was just curious that whether there is any meta-stable state in between those two temperatures. Yes, there's any metastable state, yes.
Okay, so from our resistivity measurements, only thing we found is between that region, this UI into AS is actually like a condo insulator. So from our measurement, I can say that now. But other than that,
okay, I didn't. Okay, I'll follow you later. Okay, thank you.
Okay.
Can I add one more question, please? Yeah, so I have seen your slide wherein you discuss about the Dirac state, which is rising slightly above Fermi level, right?
yes.
So you also mentioned that you are supposed to plan to shift that place and then try to bring it to Fermi level. So are you planning by doping some elements? If that is the case, which type of element do you think will be preferable?
Like maybe potassium doping would work on that as well, but our main plan for now is to perform the time resolved RPS to see the unoccupied state. So, and then we can directly resolve the unoccupied state without doping.
Okay, great. Thank you.
Savin, I have
Yes.
one more thing. Just a comment, like because your data and calculations, I think they are based upon the system being a collinear magnet, isn't it? And just to give you, like, I have seen a recent talk on neutron diffraction, and I think magnetism is not collinear. Actually, it's a helix, but very different kind of helix. So I don't know whether those group has published their data or not, but the magnetism you have shown, I think neutron diffraction contradicts with that one. So I don't know how that's going to affect your data or your final summary or conclusion. Just to let you know, from neutron diffraction, I think the magnetism is very different than what you have shown there.
Okay, I'll follow up with that.
Okay.
Yeah.
Wonderful presentation, and thank you, Savin Regmi. Move on to the next talk, which is Mon Batarai from the University of Puerto Rico, USA. A review of the relaxer ferroelectric materials for the energy storage application. You can see this one, right?
Good morning and namaste to everybody. Today I am going to talk about relaxer ferroelectric material for energy storage application. In this presentation, I'd like to discuss about the introduction of ferroelectric material and relaxer ferroelectric material for the energy storage application, synthesis of lanthanum and scandium doped PGT material, and resultant discussion and summary. Ferroelectric material have a spontaneous electric polarization in the absence of electric field, and that can be reversed by the application of external electric field. There are different types of ferroelectric material. Today I am going to discuss about the perovskite ferroelectric that has a structure of ABO3, where A cation has a ionic radii greater than B cation, and it consists of a corner link BO6 octahedra. This is a typical structure of observed P hysteresis loop of the ferroelectric material. This table shows the A side and B side cation with their ionic radii. Some of the common ferroelectric peroxides are lead titanium, lead zirconium titanium, barium titanium, barium zirconium titanium. Here we have chosen the lead zirconium titanium, where lead BF is a A side cation and zirconium titanium BF is a B side cation. The zirconium and titanium ion displaced from the center of the BO6 octahedra, hence develop the polarization in the material. This is a morphological diagram, phase diagram of PGT compound, and higher the titanium, it shows the tetragonal structure, and lower the titanium, it shows the rhomboidal structure. When x is equal to 0.5, this is said to be morphotropic phase boundary. We have chosen x is equal to 0.47, and we stabilize the tetragonal phase by substituting lanthanum and substituting with this stoichiometric formula. This is the comparison of energy density in the dielectric material, that is polarization versus the electric field. This is for the linear dielectric. This is for the ferroelectric material. This is the antiferroelectric, and this is the relaxer ferroelectric material. Basically, energy storage capacity can be calculated by the CV square by 2. So higher the dielectric constant and breakdown strength, it gives the higher energy storage capacity. And in this figure, this shaded part gives the energy storage energy density of these materials. So in the linear dielectric and ferroelectric, it has the moderate energy storage capacity, but antiferroelectric and relaxer ferroelectric can be suitable for the high energy density capacitor. Relaxer-based ferroelectric material were began study in 1960, and it has the features of possessing polar nanoregion and dispersed in a non-polar matrix. And polar nanoregion are formed due to the chemical frustration or composition induce disorder in the perovskite ferroelectric system. In the relaxer ferroelectric capacitor, it has the high maximum polarization with the suppressed remnant polarizations and high breakdown strength, and that attributes the high energy density of the capacitor. In PGT system, the relaxer behavior can be enhanced by dropping lanthanum, scandium, magnesium, barium, and niobium, etc., alone or with their compositions. Here I am going to discuss about the synthesis of lanthanum and scandium substitution of PGT material by solid state method and pulse laser deposition technique. Especially in the solid state method, we make a ceramic capacitor, and in pulse laser deposition technique, we make a thin film or nano film. This is the schematic diagram to make a ceramic capacitor. The required amount of elements are mixed with the any solvent like ethanol or methanol. Then we put for the energy ball milling, and for the 12 hour, 24 hour is the required, and that is dried for around 100 degrees Celsius. Then dried material are grinded and put for the calcination for around 1000 to 1300 degrees Celsius. And then we make a pellet in the hydraulic press, and we do the sintering around 1300 degrees Celsius. And the pellet are made with the top and bottom electrode with silver or platinum with a different technique. This is a schematic diagram of pulse laser deposition technique. It has a component. This is a target. This is the substrate. This is the laser light, and laser light hit the target, and the thin film is deposited in the substrate. And vacuum pressure around 10 to the power minus 6 with the oxygen environment. These are the parameters to deposit the thin film, and we made the LSMO as a bottom electrode and platinum for the top electrode, and we use the substrate as a MGU. This is the X-ray diffraction measurement of the ceramic capacitor and thin film capacitor. We check the phase purity of the materials with this technique. This is SCM and EDX measurement of the ceramic. So we got the grain size of the ceramic around 2 micrometer, and elemental analysis was carried out with the EDS measurement. Surface topography of thin film were analyzed with the AFM measurement, and we got around the 5 nanometer roughness of the thin film, and thickness of the thin film was measured with the profile meter. This is the dielectric constant with frequency of the ceramic capacitor. We got the dielectric constant around 1000 at room temperature at 100 Hertz frequency, and we got the low loss times N. This is the dielectric behavior of the PLZTS ceramic with temperature. So we can see the broad range of dielectric constant with temperature, and it insight into the relaxer behavior of the materials. Further, we analyze the relaxer behavior of the materials with the Curie's law quantitatively, and we got del Tm equals to around 60. It shows the relaxer behavior of the materials. Further, we analyze quantifying the relaxer behavior of the material with the modified Curie's law, and we got the value of gamma is equal to 1.94. When the gamma value is between 1 to 2, it shows the relaxer behavior of the material. When gamma is equal to 1, it shows the ferroelectric behavior of the material. So in this case, our grown material has the diffuse phase transition, and similarly, we have analyzed the dielectric behavior of the thin film compositions with the temperature. It shows the dielectric constant has the broad range of dielectric constant with temperature. It shows the relaxer behavior, and further we analyze with the modified Curie's law, and we obtain gamma value is equal to 1.96. That suggests the relaxer behavior of the thin film compositions. This is the P hysteresis loop of the ceramic capacitor. We obtain the low remnant polarization and high spontaneous polarization. It gives the high energy density around 1162 millijoule per centimeter cube with efficiency 79%. Similarly, for the P measurement of thin film, we got the slim loop hysteresis, and which turn out the energy density of the capacitor is 19 joule per centimeter cube with efficiency 66%, and this value suggests our grown thin film can be suitable for the energy storage application. This is the summary. Our work illustrates that substantial reduction in the remnant polarizations and an enhancement of spontaneous polarization with the lanthanum and scandium substitution in the PGT. That result the significant enhancement of the energy storage capacity and efficiency of ceramic and thin film capacitor. So our grown materials can be suitable for the energy storage application. This work was supported by DoD and NASA SCORE. Thank you very much. If you have any questions.
Any question for the Mohan Bhatt-Roy? Hello? Okay, if there is no question, thanks to the speaker.
Okay. Thank you very much for the listening.
So our next talk is by Vishnu Pokhrel from Prithvinarayan campus, Pokhara. He'll talk about the density functional theory study on the electronic properties of methane hydrate.
Hello everyone. First, I would like to thanks to ANPA, PRI and Nepal Physical Society for this wonderful opportunity to present my research work here. My name is Vishnu Pokhrel and I belong to Pokhara, Nepal. And I am a MSc Physics student of Prithvinarayan campus, Pokhara. Let me start with title of my work. The title of my project is A Density Functional Theory Study on Electronic Properties of Methane Hydrate. And this is my outline here, where I will focus on the result and discussion part. Gas hydrates are crystalline water-based solid structure where gas molecules are trapped inside cages of frozen water molecules, and the ratio between the water molecule and gas molecule is 85:15. There is no any chemical bonding between water molecules and gas molecule, but they are connected by hydrogen bonding. Gas hydrates are stable at low temperature and high pressure. There are many examples of gas hydrate in this universe, such as carbon dioxide hydrate, carbon monoxide hydrate, and hydrogen hydrate, etc. etc. Generally, methane hydrates are one example of gas hydrate where the composition is CH4.NH2O. N is the ratio of water molecule to gas molecule, and it varies from 5.75 to 17. Methane hydrate is often called burning ice because it looks like an ice but starts burning when an open flame is brought close to it. The possibility of finding gas hydrates in ocean is 98% and 2% on land. The suitable environments for the gas hydrates are sedimentary rock unit below Arctic permafrost, deep water sediment of lakes and seas under Antarctic ice, and sedimentary deposit along continental margin. This slide is used to describe the importance of methane hydrate. The first one is the energy stored in methane hydrate reserves twice as much as energy than in all other hydrocarbon sources. Second one is it can be used potential fossil fuel resources for the future. For the classification of hydrate structure, there are generally three types of hydrate structure. First one is body-centered cubic structure, and it is denoted by SI. Second one is face-centered cubic structure, and which is denoted by SII. And third one is hexagonal hydrate structure, which is denoted by SH. There are generally three types of cages can be found. First is small, and which can be formed from 12 pentagonal faces. And the second one is medium cage, and which has 3 square, 6 pentagonal, and 3 hexagonal faces. And the third one is large cages, and which can be formed from 12 pentagonal and 2 hexagonal faces. Okay. There are some limitation in methane hydrate. The first and most one is that methane hydrate are found in a difficult location, either under Arctic permafrost or below at least 500 meters of water. And the second limitation is that it will be difficult to utilize it properly, because methane is also a greenhouse gases. And third one is it is non-renewable sources of fuel. The objectives of this research work are as follows. First one is the determine the electronic properties of methane hydrate, like band gap, Homolomo gap, binding energy. And the most important objective is to compare the electronic properties between different gas hydrate. Here I have used density functional theory for the calculation and the analysis of the data, where density functional theory predicts a great variety of molecular properties such as vibrational frequency, ionization energy, electronic and magnetic properties, etc. And the software is a Gaussian 09 program. Job type is optimization and single point. A method is ground state and hybrid density functional theory, and the functional is B3 LYP, where basis set is 631G. The first slide of result and discussion is used to describe the binding energy per atom of different gases. And we can see that the binding energy per atom of carbon dioxide and carbon monoxide is greater than the methane and hydrogen gas. So the higher binding energy per atom of CO2 and CO, and the lower binding energy per atom of methane and hydrogen shows that methane and hydrogen are less stable than the CO2 and CO. Similarly, here we can see that the Homolomo gap of methane and hydrogen gas is greater than the gap of carbon dioxide and carbon monoxide. So it also shows that the methane and hydrogen gas are less stable. Here the left side figure is about bond length of methane hydrate, where the bond length is varies from 0.973 Armstrong to 1.767 Armstrong. And the right side is about the charge distribution of methane hydrate, where the charge distribution is varies from minus 0.858 to plus 0.858, where hydrogen has positive charge about 0.4, and carbon has negative 0.63, and oxygen has also negative charge about minus 0.8. And this calculation is done for the methane hydrate using small cage. In this slide, we can see the HOMO and LUMO orbital of methane hydrate using small cages, where HOMO orbital at the left side of the figure and LUMO orbital is at the right side of the figure, where HOMO stands for the highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. Here we discuss some electronic properties of carbon dioxide hydrate, methane hydrate, and just hydrate by using the small cage, which is formed from 12 pentagonal faces. We can see that all of these properties are similar for all of these three types of hydrate. Similar to the small cage, in medium cases, we also found that the properties are similar for these three types of hydrate structure. But if we compare the small cage structure with medium cage structure, we found that the binding energy per molecule of any hydrate using medium cage is very smaller than using small cage structure, and the dipole moment using medium cage is too large than the using small cage structure. So the conclusion made by the comparing properties between two cases is that the hydrate structure which made from medium case is less stable and more reactive than the hydrate made from small cage structure. This slide of result and discussion is used to compare the electronic energy and dipole moment of methane hydrate. This graph shows that the electronic energy is increasing with increasing charge, which is shown in red line, while the dipole moment is decreasing with increasing charge, which is shown in green line. Similarly, of the previous slide, here we also compare the electronic energy and dipole moment of hydrate only. Here we also found a similar type of graph where the electronic energy is increasing with increasing charge, while dipole moment is decreasing with increasing charge. And the conclusion for the whole project has been divided into three parts. First one is methane is more reactive than other gases, and the hydrate formed from small cages is more stable from medium cage structure, and the binding energy per molecule is increasing with increasing charge, while dipole moment is decreasing with increasing charge. And for the acknowledgement, I would like to express my special thanks of gratitude to my supervisors, Dr. Kapila Adhikari and Dr. Krishna Raj Adhikari, and to my honorable teacher, Mr. Parasuram Paudel, and to all of my honorable teachers, friends, family members, and who helped me for this research work. And this is my references. Okay. Thank you so much. Now all of you can ask questions related with my project work.
Thank you. Anybody has any questions?
I have one question. Actually, I have a couple of questions. So, first, I have a question about the choice of this functional. Why this B3YLP is used when we have better functional like PB and functional exist? First question. Second question: why don't they care about polarization and diffusion effect while choosing the best set?
Thank you so much for your question, sir. The first, the answer of the first question is for this my research, and just I use the B3LIP for the it is the most common hybrid density functional for the well-known. So I choose the B3LIP, and I will go further for the MO6 also. And I will answer the question for the second answer.
A quick question. So I see there is a difference in the homo-lumo gap for small gaps for small case and medium case, I believe. So the one has around 4 eV and the other has lesser than 1 eV. So what makes that difference? And so you mentioned that you will be looking at the transport properties. So for that higher homolumo gaps, what kind of transport properties you would be looking at? Like what would be you doing to see the transport properties?
Repeat the question once again. Repeat the question, sir. Can you repeat the question, sir, once again?
So I see the difference in the homolumo gaps between the small and the medium case. So what makes that difference in between those two materials? And what type of transport properties you would be looking since there is a large band gap on the small case material?
So the conclusion made by the comparing the small gauge structure and the large gauge structure. And we can find the small gauge, the structure made from the small gauge are more stable and less reactive than the second the using the medium structure.
Okay, let's thank the speaker, Bishnu Pokhrel. We have a last talk in this session by Avishkar Subedi. The title of the talk is The Study of the Mechanochemistry of the Silicon Carbide Nanoribbons by Using the First Principles.
Hello.
Hello.
Hello, Professor. I don't know. I can't hear anything from Professor. So can I share the slide myself? Okay. Yeah, I'll do that.
Hi everyone. First of all, thanks ANPA and PRI Pokhara to give the opportunity of participant on this program. It's me Aviskar Subedi, also member of PRI Pokhara, student of MSc 4th semester, Department of Physics, Prithvinavan campus, Pokhara. This is the outline of this presentation. First part, introduction. Second part, approach, some experimental and computational, and then methodology, calculation, and finally, result and discussion section. Mechanochemistry. It's quite clear it's from topic. In chemical process, there were many approaches like electrochemistry, photochemistry, thermochemistry, and mechanochemistry. Mechanochemistry is the study of mechanics of molecules under effect of external forces. It studies the chemical and physiochemical changes of molecule under strain. Simply apply mechanical force and observe the changes on chemical properties we call as mechanochemistry simple. To observe mechanochemistry, some experimental processes were developed. Here, AFM technique means atomic force microscopic technique. Applied force from the tip of the cantilever here. Sample of molecule placed on the center, and then mechanical changes will observed from the laser displacement from detector. Simply, it follows Hooke's law. Deformation is measured by position detector center. Magnetic tweezer. When sample of the molecule is placed under the magnetic line of forces, the distraction of magnetic line of force gives the properties of the molecule. In this way, we observe the mechanochemistry from magnetic tweezer method. Similarly, another one, optical tweezer, is also one of the famous technique to observe the mechanochemistry. Sonation and so on, other techniques there. I just mention here. Conventional approach. Usually two methods were in practice. First one is here COSEF and second one is EFEI. COSEF stands for constant geometries to simulate external forces. In this process, intraatomic bond will stress and calculate forces in terms of potential. It is first used by Weir in 2000. So it's called isometric approach. Forces include indirectly. Second one, EFEI. In this approach, we directly applied force on the molecule and study the geometry of the molecule. Nanoribbon. Nanoribbon is made from strip of graphene-like structure. It have only one atom thickness, usually white less than 50 nanometer, where we call nanoribbon. By the structure, three types of nanoribbon in practice. First one is armchair, second one is zigzag nanoribbon, and third one is chiral nanoribbon. By coordinate geometry, it's in like two-dimensional, but we treat as one-dimensional and called QG one-dimensional structure. Silicon carbide nanoribbon. Silicon carbide sheet have hexagonal or honeycomb-like structure. It is stable because of sp2 hybridization, or it try to be partially sp3 hybridization. Energy band gap depend upon their easy structure. It is suitable material for fabrication of electronic device of high temperature, high power, and high frequency application. So it is one of the interesting material on nanophysics. Objective of our research here to find the binding energy for atom under stress, to study the ionization potential, electron affinity of the molecule under stress, to study the homology energy gap for each elongated ribbon, and analyze energy gap. Computational method, we already mentioned it. We use COSEF technique here in density function theory. We use hybrid functional. B3LYP is one of the famous functional, and basis set will LA L2DJ. Because of computational cost, we use this functional and basis set. All these taxes are done in Gaussian 09 package. Methodology. We obtain energy of HOMO-LUMO gap from energy of LUMO minus energy of HOMO. Ionization potential calculated from negative energy of HOMO. Similarly, electron affinity obtained from negative energy of LUMO. Binding energy per atom calculated by this formula. Thus, positive binding energy represents the stable. silicon carbide nanoribbon. Here the figure shows silicon carbide nanoribbon. First one is the 1 armchair silicon carbide nanoribbon having weight 3.5 angstrom, and second one is the 2 armchair silicon carbide nanoribbon having weight 8.82 angstrom. 1 and 2 are the chiral vector that defines the each size of the nanoribbon. Here we most calculation were done in 1 nanoribbon. 2 nanoribbon will we just optimize and compare the each structure. These are the input file for our calculation. First one is 1 armchair silicon carbide nanoribbon having weight 3.54 and 48 atom and 318 electron. Second one is weight have 8.82 angstrom, 72 atom and 450 electron. This one is second one is just only optimized structure which shown. It shows the method of calculation. We test the molecule by taking each ring fixed. In such a way, we optimize the structure and use to find different properties. Here, the 1 silicon carbide, armchair silicon carbide nanoribbon is under study. It gives the binding energy under external stress, length versus binding energy per atom. It shows that binding energy per atom will goes decreasing when we increase the length of nanoribbon. Continuous data, and this one is second one table is 2 armchairs silicon carbide nanoribbon. Just it is optimized structure, and binding energy per atom will goes increasing here. Homolomo gap under external stress. When we increase the or stress the nanoribbon, then homolomo energy gap will goes decreasing. This table clearly shows it. This is the table of increasing length of nanoribbon and ionization potential and electron affinity. When you increase the length of nanoribbon, then ionization potential shows this data, and electron affinity goes slightly increasing form. When we stress the nanoribbon, the binding energy per atom will go decreasing. The graph shows it that clearly. It shows the stability will decreases when applied forces on silicon carbide nanoribbon. It is the plot of length versus energy gap, homolomo energy gap. When we increase the length of ribbon or stress the length of ribbon, then its energy gap will slightly decreases. It means it try to go semiconducting to conducting nature, not fully conducting but slightly semiconducting to conducting. Here the plot of length of nanoribbon versus electron affinity. The plot shows slightly increasing length of nanoribbon, then slightly increasing on the electron affinity of the molecule. The electron affinity of the molecule is the amount of energy released when an electron is attached to a neutral molecule in the gaseous state to form negative ion. The electron affinity of the molecule is a complicated function of their electronic structure. These are the plot of frontier molecular orbital. Lowercase is HOMO and uppercase is LUMO. These are just optimized structure, relaxed structure. These frontier molecular orbitals are the stress phases of the nanoribbon, and lowercase is HOMO, uppercase is LUMO. That's not changes. It shows sp2 hybridization. It's not changes on optimized and stress phases. These are the conclusion of our study. Stability decreases when we stress the nanoribbon. Binding energy per atom goes to decrease when we increase the length of nanoribbon. Stability will increase when increase in ease of nanoribbon, which was already there. Energy gap will decrease when we stress the nanoribbon. It goes semiconducting to slightly conducting nature. That's energy gap will decrease on increasing the ease of nanoribbon. When we goes 1 armchair to 2 armchair, the energy gap will be decreased. Electron affinity will increase when you stress the nano. Thank you for Dr. Kabiladikar sir, friends Mizas Tiwari, Vishnu Pokhrel, and Sanjeev. These are the references. Sorry. Thank you. Thank you all.
Thank you very much for the talk, Avishkar Suri. Any questions? We have enough time.
Yes, nice talk, Avishkar Suvedi. So I don't know much about the silicon carbide, so just out of my curiosity. The people use silicon carbide as substrates for different materials. So do you have any information on that? What type of silicon carbide as a substrate can be used so that it doesn't have any effect, kind of any pinning effect or any dipole formation effect on the sample, any stable kind of silicon carbide substrates, because you mentioned there are different types of silicon carbide substrates.
Okay, thank you, sir. Most of the research are on doing graphene recently. Then recently, most of the industries are in silicon phases. So silicon carbide is starting from why not silicon carbide? It shows the interesting properties of band gap also. So in the most of the case of fabrication for electronic device and high temperature, silicon carbide is most useful material. So it's going to study on silicon carbide, sir.
Okay, thank you, Avishkar Suvedi.
Any more questions? So let's thank to the speaker, and then I also conclude our session right now. Session starts at 10 o'clock. I'm not sure if we are in the same WebEx or different. ANPA.
We're here.
Okay, so it's going to be the same link here. So the next session starts at 10 o'clock. 5 more minutes. If you have any questions, you can fire up. And we're going to take a 5-minute break. Neil Pandeji, I think you are a host now, right?